Warm good morning to everyone. Thank you so much for being here and listening to this presentation. My name is Roberto Pereira. I am a PhD student at Auburn University at the Aerospace Engineering Department for the programs of Dr. Agarwal as my main advisor, as well as Dr. Guzzetti as my co-advisor. Our projects basically involve the integration of machine learning and artificial intelligence methods into solid mechanics, material science, and fracture mechanics of structures. Today I'll be presenting our latest work. Basically, it is a graph neural network machine learning framework that is able to dynamically emulate crack propagation, crack coalescence, as well as stress evolution in configurations involving multiple cracks from 5 to 19 microcracks. I'd like to thank the Department of Defense for funding this project through the Naval Air Warfare Center Weapons Division, through the SMART Scholarship, and as well as the Auburn University Supercomputer Easily for allowing us to use their GPU units. So what drove us to approach this problem? What inspired us to use machine learning for a dynamic prediction of crack propagation? Well, it is well known that computational modeling fracture problems is extremely important for us to further our understanding of how materials break without having to break them. Ultimately, as scientists, we want to know how things break without actually breaking them in an experiment that can save us a lot of money. There are a lot of very good computational models out there that can emulate crack propagation, dynamic crack propagation, crack bifurcation, fragmentation due to detonation or explosive, as well as fragmentation due to hypervelocity impact. These models are extremely important for us. However, as scientists, we're always trying to improve things. And one of the main challenges of computational models, specifically computational models for more complex cases involving higher dimension and such, is they're quite computationally expensive. They require a long time to converge and get the results that we want. This can take up to days, weeks, sometimes months, a lot of months, and this can be quite time consuming. So this is where machine learning comes in. Machine learning has been recently gathering a lot of interest, specifically to make things faster, make predictions faster. There are a lot of journals out there that have tackled already machine learning methods for solid mechanics and fracture mechanics and such in a reduced order modeling technique, proving that they can reduce time from these computational models. And we can make this hybrid sort of frameworks that can help us improve the current time that we need to gather some results from the computational models. One of my favorite works was published last year by Google's DeepMind company. And basically, they introduced a graph neural network representation that can emulate physics. So now they showed that we can actually predict physics using artificial intelligence. And the way they did this was combining graph theory from mathematics along with artificial neural networks. And it's shown here in the bottom how they basically were able to predict the physics, the motion of water particles interacting within a rigid body. And then they extended this work later last year into a mesh-based graph neural network where the nodes of the graph can be represented as the meshed nodes and the edges as the mesh edges. And they were able to simulate flow over a cylinder, flow over an airfoil, as well as plate bending. And the main takeaway from this work is that not only were they able to make these predictions quite accurate, but they were able to do them much faster, by orders of magnitude faster than existing high fidelity computational models that were used to gather the training data set for these. So this inspired us to say, hey, why not use this advancement in graph neural networks and try to predict a dynamic emulation of a crack propagation problem. So this brings us to the work here. And basically on this section, I'll explain how we develop the training data set, what is the problem setup that we use, and how do we make the graph representation, how do we make the graph network from the setups. So for gathering the training data set, we made use of the extended finite element method. Basically, we use a 2D perfectly brittle material with these material properties here. And to make a large training data set, we have this system here, which is 2,000 millimeters by 3,000 millimeter. We apply a constant load displacement at the top of 0.01 meters. And we say, why not vary the number of initial cracks that I have, as well as vary the initial angles and vary their initial positions. In other words, we can have our training data set can have from 5 microcracks all the way to 19 microcracks. So the number of cracks is varied. The position where these cracks are placed are totally random in this configuration, as well as their initial orientation are randomized by a 0 degree, shown here. We have 120 degrees shown here, as well as 60 degrees shown here. So we can have 3 different orientations. We can have from 5 to 19 microcracks positioned randomly in the domain. The displacement is kept constant, and the material properties are kept constant for the training data set. Then using this approach, we create 64 simulations for each number of microcracks from 5 to 19. This gives us a total of 960 simulations for the training data set, which we split by 90% and 10% for training and validation respectively. And an important thing to note here is that although our training data set is 960 simulations, each simulation can have from 50 all the way to 100 time steps. So our actual input size can go up to 96,000 discrete time steps. Similarly, we did the same approach for the test data set, and we developed 15 simulations for each number of microcracks from 5 to 19, and this gives us a total of 225 simulations for the test data set. So now I've shown you the material properties, how we gather the training data set, and on this slide, I'll show you how we develop the graph representation for the model. And basically from graph theory, to simplify the problem, what we did is we have 5 to 19 microcracks. Why not place one node from the graph at each crack tip? So now for each crack, we have 2 nodes at each crack tip. Now these nodes can have nodal features, and the nodal features that we use were their initial positions, their X and Y coordinates. We also use the initial orientation of the crack, that's another nodal feature, and we use the mode 1 and mode 2 stress intensity factors as for the nodal features as well. And this gives us basically this graph that contains only nodes. Now for the edges, what we did is we used the nearest neighbor approach, where we have this zone of influence, and this zone of influence is shown in these images as the green shaded green region. And through optimization of the model, through cross-validation, we found that the optimal radius value is 750 millimeters. So using this 750 millimeter enclosing region, we iterate crack by crack. So we iterate for each crack. We find the cracks that line within this 750 millimeters of both crack tips, and we attach edges. So now we have this graph where we have nodes, and for each node, we have edges attaching the nearest neighboring cracks to that crack. And what this tells us, what the nearest neighbor approach tells us, is that the current crack is highly influenced by the surrounding cracks that lie within the zone of influence rather than cracks that are farther away. And we did this for each crack in the system. This gives us some sort of nodes, and then we have the edges in the graph as well. So a very important application in this model is the message passing approach. One challenge that we came upon when working on this was that our input is always changing size. And in machine learning, changing size of inputs can be challenging because your model usually can only be trained for a fixed size. So to take care of this, we use the message passing approach, where now it doesn't matter if we have 5 cracks or 19 cracks, both will have a different input. But also when we have one configuration of 5 microcracks, it will have a different neighboring configuration than another simulation of 5 cracks. So the input even changes for the same number of cracks. So what the message passing approach does is we apply an embedding. Basically, we have the nodal features. Initially, we pass them through a multi-layer perceptron network for the nodes called VMLP. And this multi-layer perceptron network basically transfers the nodal features and gives us this embedding which describes the nodal features in the latent space. We apply the same thing for the edges, where we have this EMLP. We pass the edges features there, and we get this embedding for the edges in the latent space. Finally, we concatenate these two, and we pass it to an additional MLP network, which we call the GMLP, stands for Graph Multilayer Perceptor Network, and it gives us this one-hot encoded feature vector. And what this one-hot encoded feature vector says, it's describing the relations that exist between the nodal features, or the nodes, and the edges features in the latent space. So it describes this relationship between the two in the latent space, and it is a fixed size. So now we can evade the varying input size challenge. Then the message passing approach does this multiple times, which is called the number of message passing steps. Depending on the complexity of your problem, you may need more message passing steps. But however, through optimization of the framework in cross validation, we found that the optimal number of message passing steps for this work was 6 steps. So we repeat this 6 steps, and we get this one-hot encoded feature vector in the latent space. And basically, this gives us, I've already explained how we gather the training data set, the problem setup, how we developed the graph representation of the problem, and how we overcame varying input size challenge. Now we'll go over the actual architecture of the framework shown here. I will go in this through each box in this framework in detail in the next couple of next slides. But this just wanted to give you a brief idea of how it works. Basically, a main takeaway is that our input involves the 4 previous time steps. So we have t-3, t-2, t-1, and t. We generate the graph. We apply the message passing approach, and we concatenate this. And then this is what we do here. This is a message passing approach. I concatenate. Then we have 2 graph neural networks, or our framework involves 2 initial graph neural networks called K1 GNN, K2 GNN. And what these do is they predict the mode 1 and mode 2 stress intensity factors at the next time step, at t+1. Given t-3 to t, we predict t+1 for the mode 1 and mode 2 stress intensity factors. The predicted output from these 2, we pass it to the class GNN, which predicts the quasi-static nature of the problem as qt+1 at the next time step. Then we concatenate all of these predictions, and we pass it to our last graph neural network called cprop-GNN, which actually propagates the crack to the next time step. So this first box is what I explained in the first slide, the first section, where we get this one-hot encoded feature vector describing the nodal and edges features at the latent space. Moving on, we get this one-hot encoded feature vector. We pass it to the K1 GNN separately from the K2 GNN, and both of them predict the mode 1 stress intensity factors at the future step, and the mode 2 stress intensity factors at the future step. And we thought this would be a clever idea for the problem, because rather than trying to predict the crack propagation without the K1 and K2, why not give the framework some physical meaning of the problem itself prior to predicting the next position of the cracks. We thought that this would be a good idea. And also, the main takeaway is now not only can we predict the crack propagation, but with K1 and K2, we can use linear elastic fracture mechanics equations to obtain the stress distribution or stress evolution in the material. Moving on, we get the predicted K1 and K2. We pass it to the class GNN. And what the class GNN is a binary prediction of the quasi-static nature of the problem. In quasi-static loading, where the time is very discretized, only one crack tip is allowed to propagate per time step. So to predict the quasi-static nature of the problem, we use the one-hot encoded feature vector, the predicted K1 and K2, and we try and predict the propagating crack tips as 1 and the non-propagating crack tips as 0s. Finally, we get all of these outputs. We pass it to the last GNN called cprop-GNN, which gives us the position of the crack tips at the future time steps using all of these predictions, as well as the information of the previous graphs. So I've explained already the configuration of the problem, the graph representation, the message passing approach, as well as the entire architecture of the framework. And now I'll show you some of the exciting results that we obtained in this work. So what we see here is on the left, we have 8 microcracks. On the right, we have 10 microcracks. So these are different configurations. And these are animations. I just wanted to show some qualitative results, animations of the framework at work. Basically, so if we look at 8 microcracks on the left, we have this sort of a crack propagation history. And you can see that as the color becomes more red from dark blue, it's arriving to the final time step. Similarly, on the right, we have the stress evolution in the material, which is being predicted. And again, we are comparing extended finite element method to the graph neural network prediction. And on the bottom is I'm just trying to track how these cracks labeled here from 1 to 3, how each crack is propagating at each time step, how is it increasing, how is the length of that crack increasing. And similarly for 10 microcracks. I could not show all of the simulations from the test data set because it's 225, but I'm showing here these 2. And if we move to the next slide, I'm showing also for 12 microcracks and 19 microcracks, so a little bit more complex cases shown here. The main takeaway here is that if we compare the extended finite element method to the graph neural network results, qualitatively, they seem identical. So the predictions are quite accurate. But now I'll move on and I'll show you some quantitative results. So the first quantitative result error analysis that we performed was for the prediction of K1 and K2 GNN. And for this, we use the effective stress intensity factors. And the effective stress intensity factor is an important prediction because it tells you essentially, it defines the propagating cracks. So the crack tips that have a stress intensity factor that's larger than the critical stress intensity factor are more likely to propagate. Similarly, if you have 2 cracks like shown here, and this crack, you can see that they probably have a high effective stress intensity factors between them. So at the next time steps, these 2 cracks are more likely to connect. So what you see here at the top, it is an error analysis on the entire test data set from 5 microcracks all the way to 19 microcracks. And we see here 15 discrete points. And what this represents is the maximum average error for the effective stress intensity factors for each simulation in the test data set. And the main takeaway is if we look at 6 microcracks, is the highest percent error, and it's well below 3.5, I would say approximately 3.4% error. So this is very low error, so we can conclude that the predictions for the K1 and K2 are very accurate from are predicted with good accuracy by the GNN on this test data set. And another very important point to make is that you would expect intuitively, you would expect the 19 cracks to have a higher error, but this wasn't the case. In this case, 6 microcracks had the highest error in our test data set. So moving on now, let's try to do a similar error analysis on the crack propagation. We have done an error analysis on the mode 1 and mode 2 stresses, and now let's do the error analysis on the crack propagation. So I just show these plots here to explain how we made this plot. Basically, we have the prediction here on the left, and then we have the prediction here on the right, and then we have the extended finite element method on the left. Then we see these crack paths, and these are the crack coalescence and crack propagation. So to make the error analysis, what we did is we create a spline interpolation for the final crack path on both the extended finite element method as well as in the GNN prediction. This gives us a lot of points. And then we take the difference between those 2 spline interpolations, and we take the maximum distance error, and that's what you see here. That's the point you see here. So we're using the maximum error in the crack path, prediction. And basically, similar to before, we have from 5 to 19 microcracks, and you'll see 15 discrete points, which would correspond to each simulation in the test data set. Again, intuitively, you would expect 19 cracks to have a higher error, but for this case, 12 microcracks was the one with the highest error at approximately 2.6%. So this is a spatial deviance error analysis, and on the bottom, you have a time-dependent analysis So how does the error evolve in time? And what you see here is you have from crack A all the way to crack F, and these are labeled here from A, B, C, D, E, and F. And these are from 5 all the way to 19 microcracks. And on this case, the higher error was for the case of 19 microcracks at approximately times step 43, and it's approximately around 2.9% error. So still very low. So what these results tells us is that the graph neural network, it makes very good predictions. So the predictions have very good accuracy, and we can use that with confidence. So now this is the question: why use the graph neural network? That's the next question for us to ask. Why not use the extended finite element method if it will give you still results and you don't have to rely on this small errors? Well, we did an analysis, a time analysis of how long does the extended finite element method take to generate simulations, and how long does the graph neural network take to generate simulations. The extended finite element method is shown in this red dots, and the graph neural network is shown in this green dots. And what you can see immediately is that there's a huge time improvement using the graph neural network. Actually, it is a time improvement from 5 times to 20 times faster using the developed graph neural network. So basically, if you have a very large system, a lot of configurations to consider, you may want to use the graph neural network because it will give you faster simulations. Now, if you have a smaller number of simulations that you need, the extended finite element method may become in handy, given that the training time for the graph neural network was approximately 5 hours. We use a batch size of 32, and we use 4 NVIDIA Tesla P4 GPUs, thanks to Auburn's supercomputer easily. And this time here is only for 1 epoch, and we use 5 epochs for training. So we have to multiply this times 5. This gives us approximately 5 hours and 10 minutes. So in the case that you have very little number of configurations, the extended finite element method will outperform in time the graph neural network. However, if you're working with thousands of configurations, maybe even hundreds of configurations, then the graph neural network may be faster, may be a better choice to have in this case. So yeah, this concludes my presentation. These are some of the references I included in the initial slides covering the Google DeepMind work with the graph neural networks. 2 of them cover here. We also have the fragmentation experiments, the crack bifurcation experiments that I showed in the beginning, and some of the computational models. Thank you so much for staying tuned, listening to this presentation. And I would also like to thank Department of Defense, through the Naval Air Warfare Center Weapons Division, through the SMART Scholarship for funding this work. Thank you, and I will be happy to answer any questions